Good day, statisticians. In this video, we're going to continue where we left off in the last in thinking about regression to the mean, and this is regression to the mean part 2. But in particular, our goal in this video is going to be to develop the actual equation of the least squares regression line based on regression to the mean. So let's start with an example based on what we were doing in our last class. Here, I found a cute little data set that was took a random sample of some married couples, some husbands and wives, and it asked people how old they were when they got married, and we got this scatter plot. And interesting enough, there seems to be a relatively strong association between the age of a husband and a wife, at least in the sample. So kind of made me think a little bit. I was remembering when I got married, I was 23 years old. Fun fact, 23. And so it made me think like, oh, well, you know, what would, and based on the data in this data set, what would have it predicted would be the age of my wife based on how old I was, 23 years old? Well, I don't quite have enough information to make that guess, but check it out. Here, I know some data about at least the folks in the sample. In the sample, the husband's average age was 34 and a half, and the wife's average age was 32.4. So clearly, getting married at 23 was younger than average here, right? So I'd probably have a below average age of wife, wife less than 32.4 years old. But let's make a prediction. So to make our prediction, remember, it was all based on the relative distance of values to the mean. So I could start off by saying, okay, if I want to predict the age of a wife, let me start by focusing in on the husband who is 23 years old, right? And I got to convert that to a z-score. What is the z-score? How far below average was I when I got married? So I could convert that to a z-score. All I need to do is take that 23 and subtract the average, which was 34.5 years old, and divide it by the standard deviation, 12 and a half. So let's see what we get there. Let me plug it into my handy dandy calculator. That'd be 23 minus 34.5 divided by 12. Divided by 12.5. That's negative 0.92. So that would mean, right, that my age, 23 years old, I was 0.92 standard deviations below average, at least compared to the folks in this sample. All right. Now, from that, we can say, okay, what would be the predicted z-score? So I'm trying to make a prediction for y. I wanted the predicted age of the wife. And so from this, I know that the z-score for the predicted y value based on regression to the mean is going to be basically the same as the z-score for the x value, however, scaled back, regressed to the mean by the factor of r, by the correlation, right? And so I can say, okay, what was R in this situation? I see that R is given to us. There was a 0.86 correlation. That was in fact a fairly strong correlation. And we know that the z-score for the 23-year-old was 0.92 standard deviations below average. I don't know why that bothers me when I don't keep colors consistent. So let me simply calculate this now and say, okay, what would be the z-score of the wife? 0.86 times negative 0.92, and I get negative 0.7912. All right, so this regression to the mean says that if I'm going to make a prediction for the wife's age, it's going to be 0.7912 standard deviations below average for the wife. So therefore, my predicted y is going to be, take the mean of the y, subtract 0.7912 standard deviations. Now, the standard deviation for the age of the wives, at least in the sample, was 11.1 years. So let me plug in those facts. That's just going to be the mean of the average age of a wife was 32.4. I'll subtract 0.7912 times 11.1. And what do we get? Syntax error. What did I do there? Do I need a I had a closed parentheses with not an open parentheses. 23 point, is that right? 23.6 or so years old. 23.6 years old. And so, fun fact, for me being 23 years old, this, based on this data, it predicts that my wife would have been slightly older than me. 23.6 years old. And fun fact, my wife, when we did get married, was older than me, actually older than me by almost about 2 years, so a little bit more than predicted here, but nevertheless. We can find the residual, but that's fine. So that's a review of all of this is stuff that we learned from our last class. But imagine this. Suppose that the correlation was actually perfectly strong instead of just pretty strong, right? How would our prediction have changed? You know, what would we have predicted in that case? Well, if it was perfectly strong, then what would change happens right here in thinking about what we would expect to be the z-score, right? The z-score of our predicted y value. Because remember, we multiplied by r, right? We had to regress back to the mean because the association wasn't perfect. But in the situation where we have a perfectly strong association, that would mean that r equals exactly 1. And if r is exactly 1, shazam, that means we don't have to regress back to the mean at all. So in that instance, we would have expected the wife to have been exactly as far below average as the husband was below average. So that would be 0.92 standard deviations below average. In that situation, if it was perfectly strong, which it wasn't, then we would have simply gone down, 32.4 minus 0.92 times the length of a standard deviation. If only I could type things in my calculator correctly today. That would say 22.188. So if there was a perfectly strong correlation, then the wife would have been just as far below average as the husband. But of course, it wasn't exactly perfectly strong. It was 0.86. So that's the idea of regression to the mean. We make our predictions a little bit closer to average when there's a less than perfect association between our variables. Okay, now let's go a little bit deeper here though, because it's kind of annoying to make our predictions like this. Typically speaking, when we make a prediction, you learn to do this probably even in Algebra 1, you did it just by getting the actual equation of the line of best fit. And we know that if we had a bunch of data, we could just throw it in our calculator here. We could hit stat calc option 8, right? And we could just throw numbers in a list and we should be able to generate the least squares regression line, the line of best fit, to make predictions. So how can we generate the actual line of best fit using regression to the mean? Well, that's what we're going to think about here in the rest of this video. So let's think about this. What would be the slope of the line of best fit? What would be the slope of the line of best fit? Well, we actually have enough to figure it out. Because let's just think about what slope means, right? So back in Algebra 1, we talked about the slope. The slope of a line is simply a ratio of how much the y variable is changing for every increase in x, right? So for how much, the slope is the change in your y variable divided by the change in your x variable, right? And so let's think about this. All right, in this situation, we know that, for instance, when the x variable goes up 1 standard deviation, right? 1 standard deviation right here. So say this was like 1, right? 1 standard deviation. Then, let's see, the standard deviation of x. If x goes up 1 standard deviation, how much would the y variable be predicted to go up? Also 1 whole standard deviation? Well, no, remember we regress back to the mean. So if x goes up 1 standard deviation, right, then y is going to go up not a full standard deviation, it's going to go r times that standard deviation, r times the standard deviation of y. And therefore, the standard deviation, right, the slope of this line should just be the change in y over the change in x, r times the standard deviation of y divided by the standard deviation of x. So let's just check that out. So that would be 0.86 times 11.1. And let's divide that by 12.5. And I got, check that guy out, 0.76 or so, roughly speaking, right? Boom. So that is what we could best estimate to be the slope of a line. So if I was to graph that guy on there, right, it's kind of hard to verify that we're correct, but that would appear to be the slope of that line. Now, once you have the slope, it would be nice to say, get the whole equation of the line of best fit here. So how could I come up with the line of best fit? Well, if you remember from regression to the mean, there's always a particular point that is on the line of best fit. What's the point that's always on the line of best fit? You guys remember? Yeah, it's kind of like that fulcrum point. Remember, it's called regression to the mean. Is that a good hint? Yes, it's the point mean x, mean y. right? So once we have the slope of the least squares regression line, then we can just use this fact that the mean x, mean y is also on the least squares regression line. And from there, we can actually get the whole equation, right? And so, I don't know, you guys remember how to do some algebra 1, some point slope kind of thing here, right? So we could say like the predicted y value minus the mean of y in this instance was 32.4, right? Should equal the slope 0.76368, right? Oops. Parentheses that way. Why would I make parentheses going the opposite way? What am I thinking today? I still have a foggy brain, I think, from being sick. And then x minus the mean of our x value is 34.5. That's just point slope. Just remember that from algebra 1. And we could do some, that's kind of ugly version of an equation right there. I don't really like it that much. So we could do some simplification. And this, my friends, is apparently the equation of that line right there. If I'm going to predict, right, where y is the age of a wife, x is the age of a husband, based on this data set, if we had similar folks in whatever situation that they're in, assuming, people are similar to those in the sample, we can predict the age of the wife will be 6.05304 years old plus 0.76368 times the age of the husband. And really, really nice. Notice that this equation was generated entirely by concept of regression to the mean. Now, wouldn't it be nice, though, if there was like a simpler version of the formula so that we didn't have to sit there and like reason our way out to everything? Couldn't we just maybe summarize this in like a couple of ways? Well, of course we can here. Let's summarize these facts here. So in general, there's a couple different ways we can write the formula for the least squares regression line. I like this way using the parameters B0 and B1 because that's kind of consistent with higher level statistics class. Though you also, in our calculator, the form of the least squares regression line is always A plus BX. And so in this instance, if you use y hat equals A plus BX, or as my preference, B0 plus B1x, either one is just the same. So you should write this down. If you're not writing things down, you should, right? The slope, B1 of the least squares regression line is always r times the standard deviation of y divided by the standard deviation of x, which hopefully was kind of intuitive to us when we just think of the fact that slope is the change in y over the change in x, right? So the slope is always r times the standard deviation of y over the standard deviation of x. Now, the y-intercepts, you could use point slope, but we can deduce that the y-intercept, B0, is always going to be just the mean of the y minus B1 times the mean of x. And so from these two facts, right, we could very quickly generate the equation of the least squares regression line without sitting there and deliberating and remembering all the principles of regression to the mean. The principles of regression to the mean lead to this equation. All right, let's just do an example. Why not? You guys want to do an example? Sorry, too bad. you know what I say. You have to just do it because I plan on doing it anyways. All right, so I suppose you could just turn this video off. Don't do that. Finish the lesson with an example here. So here's a kind of fun situation that I came across. I was talking to someone who lives in New York, and they were living in Nassau County and telling me about how much apartments cost there, and they said it was very expensive. So it made me wonder, like, how much does it cost to rent a 1,000 square foot apartment in Nassau County, New York? And 1,000 square feet, that's like not that big. I mean, I don't know. It depends on how many people you got living there, but there's no way I'd like to live with my family of my wife and 4 kids in a 1,000 square foot apartment. But so anyway, but how much would it cost in Nassau County? Well, so I got some data, and I looked at the square footage in the rent, and I found that there was interestingly a correlation, fairly moderate correlation between the square footage and the cost. I just noticed this. Whoops! When I was editing this, I forgot to change the Y. I was editing my PowerPoint, forgot to change weight to rent. I never noticed that. That's pretty funny. Anyway. So here we see that the average square footage of apartments, at least in a small sample, I think there was just 10 examples in the sample, but the average square footage of those in the sample was 845 feet. And the average rent of the apartments or whatever the other rental properties that were here, the average rent was $1,555, which is decent. It's a lot of money in my, I don't know. It seems like a lot. And of course, we would predict based on regression to the mean that if there was an 845 square foot apartment, that the cost of the rent would be $1,555. That seems kind of steep to me. I don't know. Yeah, that seems pretty steep. I remember first things have gotten more expensive. I own a house now, and yeah, it seems like kind of steep. So all this was based on this data, this set of data right here, where we have the scatter plot, and you can kind of see that moderate association. And here's the equation of the least squares regression line. So if we go to 1,000 square feet for an apartment, we can kind of just go eye up across here, and it's looking like maybe, I don't know if I'm eyeing this up right, like maybe around $1,700 or so a month for 1,000 square foot apartment. Well, let's do the math and figure it out, and let's just do it by generating the equation of the least squares regression line. So let's just generate this guy. All right. So let's start off by getting the slope first. So if I want to predict, right? Here I'm going to do it in context. Let's say I want to predict the rental price, which is not the weight. I hate when I make mistakes. Not the rental price, plus B naught times B naught plus B1 times, let's see here, this would be the square footage, the number of square feet of the apartment. We can get the slope first, B1, and it's simply going to be R times SY over SX. So let's just plug in some values here. What do we got? R was 0.665. The standard deviation of Y, the standard deviation of the rental prices, not the weight. It annoys the heck out of me. I hate things like that. I wonder if I caught the marker. Did I catch it? I'm going to do this after the video, so you'll let me know. Divide by the standard deviation of, I just noticed there's another typo there too. I have the standard deviation of Y written up. Whatever. That one's not as bad. 239.65. I hate typos. They're not as bad as like actual mistakes though. 1.0977, blah, 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 blah. Let's just write that as 1.0978 or so. Usually 4 decimal places is sufficient when we're doing this. So there we got our slope, right? All right, and now we know that we can get the y-intercept and we could prove that this formula holds, right? But it's just based on point slope. The y-intercept B naught is going to be the mean of the y minus the slope times the mean of the x. So let's just plug that in. The mean of the y, we see here's the average price of an apartment amongst those sampled here in Nassau County, New York, we're at $1,555. We'll subtract from that 1.0978 times the average square footage of an apartment there, 845 square feet. And let's see what we get. But I got 627.3841. 627.3841. And so this is supposed to be my y-intercept. So what is theoretically the equation of the line? Well, I did do this earlier. Let's see, did it match up with what I got here? Yes, the predicted rent should be the y-intercept, $627.3841 dollars plus 1.0978 times the number of square feet of that apartment. So, all right, we have our equation. Let's use it to predict how much are we gonna have to pay for that 1,000 square foot apartment. So let me just plug in 1,000 for the square feet. So that would be, I'll take this guy and I will add to it this guy. I'm just doing lots of copying. Forgive my laziness. $1,725.15. So it predicts that if you have, right, a 1,000 square foot apartment, if X is 1,000, then it predicts that the cost of that apartment will be $1,725 and about 15 sense, which to me means I probably won't be living there ever. Actually, I know for a fact I'm never going to live there. I'm very happy with where I live right now. And if I moved, it wouldn't be to Nassau County, New York, for lots of reasons, but probably not because I don't, it seems expensive. I don't know. Maybe I'm out of touch. I don't know. Either way, there you go, folks. This is a nice example of how the concept of the regression to the mean, right? The concept of regression to the mean allowed us to come up with the kind of intuit what would be the formula for getting the slope of a least squares regression line, and then using some algebra skills to have it make sense that these are our formulas for creating the line of best fit, the least squares regression line. And really this kind of like marvelous fact that I'm just going to sort of gloss over that maybe we can just reflect on, that we in a previous lesson, we talked about least squares regression and how the line of best fit minimizes the sum of the squares of the residuals of our predictions. And it's kind of amazing that method, that the minimizing the sum of the squares of the residuals actually is best accomplished by using regression to the mean. Regression to the mean accomplishes least squares of our residuals, which is kind of neat. We could just maybe reflect on why that is, but it's pretty cool. Anyway, statisticians, have a very beautiful day. I hope this lesson was useful to you, and I won't see you tomorrow, but I'll see you soon. Adios.